All right, and the last case we need to consider is the case of complex conjugate roots, or alternatively, the negative discriminant, right? So if the discriminant of the quadratic form is negative, right? So on the one hand, it means that there are two complex conjugate roots, right? But on the other hand, it means that if we complete the square, so let me give you an example. Um, let's say, what if we have something like z squared plus 4z plus 29, right? So in this case, the discriminant is 4 squared, which is what, 16 minus 4 times 29. Well, it is clear that it is negative, right? I don't even have to calculate it, right? But in that case, it means that when we complete the square, when we rewrite it as z plus 4 over 2 is 2, 2 squared plus, okay, 2 squared is 4. To get 29, I need to add another 25, I believe, right? So 25. Right, so it means that when you complete the square, you will get that your quadratic form is the z plus minus something squared plus a positive number, right? So, and basically because of that, when you integrate the reciprocal of az squared plus bz plus c, you're going to get an inverse tangent. Again, I'm going to give you an example. So the same example as before, so z squared plus 4z plus 29, which is, as I already wrote, z plus 2 squared plus 25, and 25 is 5 squared, right? So when I integrate 1 over this, z squared plus 4z plus 29 dz, I'm going to get, well, dz over z plus 2 squared plus 5 squared. Now, um, in order to get the inverse tangent, I should get something like, let me write it here. So the antiderivative of 1 over 1 plus x squared dx is inverse tangent x plus constant. All right, so in order to get something like this, I need to have 1 plus something squared, right? So to have 1, I need to factor out 5 squared, right? So this is going to be equal 1 over 5 squared times dz 1 plus z plus 2 over 5 squared, right? And this is 1 over 5 squared times, now I can get the inverse tangent. Inverse tangent of z plus 2 over 5. It's just that if I differentiate the inverse tangent of z plus 2 over 5, then I'm going to have to multiply by 1/5, right? And if I multiply the whole thing by 1/5, I'm going to get 1/5 of what I want. So in order to account for that, I need to remove the square. All right, so this is the answer, plus a constant. All right, so this is what we are going to do in the case when um, the discriminant of the quadratic form is negative. All right, so here is the general formula with alpha and beta. And then basically we can continue. So then uh, after after this, we are going to, well, essentially, this is the integration. So now we're going to multiply by beta. And then we can apply tangent to this thing, to the both left hand side and the right hand side, and then we're going to make z the subject and solve for z and so on. Well, this is pretty straightforward. It is probably a long calculation, but there is no rocket science here, so I'm going to skip it. So here is the equation for z, and the next thing is to recall that z was in fact y prime over y, and then I'm going to replace z with y prime over y, and then I'm going to integrate again, right? So y prime over y is this. Then again, y prime over y is a logarithm y prime, well, absolute value of y prime. So I'm going to have to integrate the right hand side, and the antiderivative of tangent is the logarithm of the cosine. So basically here is the expression for y. The remaining part is to simplify it, and the kind of the subtle thing that to look for um, is that we have two absolute value signs here, and in order to solve it, you kind of need to um, figure out what to do with the absolute values. Right, so this is the absolute value of y. Um, so here I apply the exponential function to the both left hand side and the right hand side. All right, so then removing the absolute value, I'm going to get plus minus sign, and then I'm going to continue. Then I'm going to take out certain things, and then finally I'm going to get the desired equation. Right, so precisely the equation that we claimed in part two of the lecture. Okay, so that was all about justification of the method to solve second order linear differential equations with constant coefficients.